So today we're going to be looking at electrostatic acceleration and deflection of the electron. So in this lab we have a cathode ray tube and a power source and a multimeter to measure our voltage. A cathode ray tube works by burning off electrons on a heating element, which is over here as you can see, and then accelerating them with a very high voltage. So the part of the CRT is also referred to as the electron gun. The electrons pass through oppositely charged plates, deflection plates, which is right here, these two plates, and which gives us a deflection acceleration. So what happens is it hits the screen, the beam of electrons, and what you can do is you can measure the displacement, which is the height of these electrons with this ruler. So here, when I turn my power source on, I can see that it's reading a voltage. This is what happens if I change this knob, which is the voltage acceleration, which this increases the intensity of the light beam, of the electron beams. And over here we have the voltage deflection, which when I increase or decrease it, it will change the height of the electron beam. So as I'm turning the voltage acceleration knob, it intensifies the electron beam. And as I'm decreasing the voltage deflection, it decreases the delta Y, and then as I'm increasing it, it increases the delta Y, the height of the electron beam.
The voltmeter is connected to the voltage of acceleration, so that as we increase and decrease this knob, we'll see the value of the voltage of acceleration on the voltmeter. Okay, so the goal of this lab is to find the relationship between the deflection voltage and the total deflection of the electron beam, which is the delta Y. In order to do this, we conducted 3 experiments. Each had a different voltage of acceleration, and with each voltage of acceleration we took 5 voltages of deflection, and with these values we made a graph to represent the relationship between the two. So before starting the experiment, you're going to want the acceleration voltage knob to be turned to 0, as well as the voltage of deflection. You don't want the power supply to be turned on or connected just yet. And as well, you don't want to make sure that there are no cracks on the bulb, because there's a gas inside that allows us to see the electron beam when you turn the voltage of acceleration. Okay, so to connect the power supply to the cathode ray tube, you're going to want to connect 1 wire or 2 wires from the power supply, like so. You're going to want 2 wires at the cathode and anode of the voltage and deflection knob, as well as 2 wires connecting at the terminals of the voltage of deflection. And you're going to set them up according to this diagram, where A connects to A, B connects to B, and so on. And it should look like this at the end. So this is A, this is B, yeah, this is D, which connects to this, and you got F for the other side. Like that. To know the values of the voltage of deflection, you're also going to want to connect a voltmeter to the terminals of the voltage of deflection, like so. Okay, so the goal of the lab is to find the relationship between the delta Y and the V of deflection over the V of acceleration. And by finding the values using the machine here, like as stated beforehand in the introduction, we can find that it is a linear formula between the two. And in this equation, we also have 3 constants: the length of deflection, which is L, the separation of deflection plates, which is the small d, and then the distance from the plates to the screen, which is the large D. So if you look on the cathode ray tube, the large D is going to be from the distance from the plate to the end here. The small d is going to be the distance from the top plate to the bottom plate, and then the large L is just going to be the length of the plates.
So as you can see, the relationship between delta Y and the voltage deflection is a linear relationship.